From the fields of Northeast Texas to the streets of Silicon Valley and all points in between, welcome to Maxim Webinars. I'd like to thank everyone for joining us today as we talk about when and why system reliability matters. Leading today's discussion will be Carlos Rodriguez, a business manager in the Micro Software and Embedded Security Group. Now, as a reminder, your microphones are muted and your cameras have been disabled during the discussion. If you want to ask a question, please type it in the questions box in the GoToWebcast application window, and we'll be sure to get to that at the end of the webinar. Now, if you want to download the presentation, there's an icon. It looks kind of like a piece of paper over on the right-hand side. Click on that, and the presentation will be downloaded to you. I think those are all the preliminaries. So with that, we'll begin today's webcast. Take it away, Carlos.
Thank you, Ben. So before anything else, I kind of want to tell you guys a little bit about myself. My name is Carlos Rodriguez. I'm a business manager here at Maxim Integrated for the Low Power Micros group. And today, like Ben mentioned, we're going to be talking about not only this new micro that we're just recently introduced, which is the MAX 32670. The MAX 32670 is part of the Darwin family, which is our low power micro family. But we'll also talk about the importance of system reliability just within any applications that you guys are working on, any type of products that you guys are designing at the moment. So let's go ahead and get started here. The first question I'm going to ask here is, when is failure not an option for us whenever we're designing? Essentially, you know, I think this is a bit of a funny question, because in reality, failure is never really part of our or something that we want within our systems. So, but you can think maybe of a laptop example where, you know, your laptop is working you're working on it every single day, and that laptop can potentially have failures every now and then, whether it's in the, you know, maybe some data getting corrupted, some of your files getting corrupted, maybe some of the code is not really working within one of the applications that you have, or maybe you're trying to connect your laptop to share your screen in some type of device, some type of like maybe bigger screen, a projector or a TV, and things can go wrong within those scenarios, right? But essentially what we can do in this case is we can simply reset the laptop to make sure that it comes back to its original state, so that it works back again and it comes back to everything going back and being normal. Right now, this is not always the case. We don't always have this luxury of having a manual reset and having being able to reset the device that we're working on, that we're designing. So what I'm going to do here in this slide, I'm going to kind of mention 4 different scenarios where this might not be possible, and where reliability really has to be at its top notch, where we have devices failing the least amount of times possible. Even though we do have a, you know, the reliability that we have right now is good enough, for some application, it really has to be at its peak. So the first example I'm gonna mention here that we have to think about it whenever we're designing our products is, you know, difficult of accessibility of that device. We can think of agricultural IoT nodes or industrial IoT nodes where we have sensors. One of them is we're going to have a bunch of sensors, hundreds of sensors across like a field or across a manufacturing facility. But also, these things are going to be in the middle of nowhere, and they're going to be really hard to get to it if something goes wrong with either the code being loaded into the sensors, into this microcontroller, essentially, that is going to be part of the sensor node. And then also maybe there might be some issues that are going to make the functionality of the data being collected by that sensor to not work anymore. The problem with that is that we're not going to be able to go to the middle of the field to be able to reset that device, especially when you have hundreds of this. It might not be very sustainable to do so. So that's one example. The other example here on the industrial IoT node, maybe the location is not so far away, but maybe the placement where the sensor is located is not very easily reachable, which means now you're going to have to possibly stop your manufacturing facility, or at least that manufacturing process that you have running at the time, and maybe take some parts away to really be able to get into this node and restart that device. So think about that whenever you guys are designing your application. Is it really easy for me to reset that device like I can in a laptop, where I can just reset every number of days in case something goes wrong, or is it going to be a lot harder to do so? So that's one example. Going here to the next block that we have robust communication. A good device where you really have to make sure your communication is very reliable is in emergency response devices. These devices are maybe not being used every single day, but whenever you need them, you want to make sure that they're working correctly and that there's no issues with that device, so that if someone calls for help, the emergency responders are able to receive that information, that emergency call, correctly, and they can take action after that. So that's another possible scenario where things could go wrong. The third scenario that we have is continuous crucial processing. We have a lot of devices that really can't stop for a single minute. You know, if an example for this one would be a pacemaker. So a pacemaker, you know, you have this device inside a person, and it's making sure that your heart is running at the proper number of beats per second, and so on. And any type of failure within this device could be one, it could bring health problems to the person that is wearing this device, that is using this device. And more importantly, it could be a lethal consequence if things go wrong with this pacemaker. So obviously, this is a great example for reliability and making sure that your system doesn't fail during the lifetime of the device. And then the fourth example here that we have to think about is valuable stored data. So a lot of the times within our devices, we have information that we're storing that, one, cannot be gained again or collected again, and two, maybe information that is just there that you want to protect, like in the example of a crypto hardware wallet, right? In that scenario, you have private keys that are essentially giving you access to your cryptocurrencies. So if that location of the memory where you have the private keys stored gets corrupted, this could potentially mean that you don't have access to your money, which is, I think everybody would agree that this is important to think about in this type of applications. So as you can see, if you kind of look through all of this potential scenarios where reliability is important, there's three main things that can go wrong. Is one, the code might be an issue. You know, there's corruption of the code, which means you're gonna not produce the output that you want within your device. Two, you're gonna have the data stored in the device could get lost, could get corrupted. And then the third scenario would be during communication of the data, that communication path stuff could go wrong between point A to point B of that information going from one place to the other. So what we have to think about here again is think about your device, think about if this is something that you guys are concerned about, and see if there's solutions for this. And I think this is where Maxim is going to come in to solve those problems. So now let's go a little bit deeper here on, you know, we've been talking about all of these issues that could potentially happen within a system, but let's talk about what exactly is causing these issues. The first thing that I want to bring up here is alpha particles. So there's alpha particles in cosmic rays, which come from space. They basically rain down, hit the Earth, and a lot of the times, these cosmic rays hit our electronic devices. And whenever this alpha particles hit the electronic devices, it can cause a lot of bit flips within the memory, and potentially causing issues with one of the three areas that we mentioned earlier, right? Either the code getting corrupted, some of the memory being stored getting corrupted, or during the communication of the device, maybe it's not outputting or sending the correct packet because something was funky within the device after these alpha particles hit the memory. So I think we have to understand this in order to be able to see what we can do to solve this potential issue. And one thing to note here too is that the larger the memory is within your microcontroller or your product in general, you're gonna have an increased likelihood of bit errors happening. And the reason for this is pretty straightforward. You have bigger area within your memory, which means that you're gonna have more higher probability of alpha particles hitting that area, which means it can cause bit flips within your system. So definitely a big problem, and this is where we have to really reset our laptops, reset our phones to reset the memories so they go back and start working again. But if we don't have that luxury of doing that, the answer to this question is going to be incorporating ECC, which is error correcting code, into our memories. ECC, what it does, for those of you guys that are not familiar with this, is it's going to allow you to detect bit errors within your memory, so the exact location of where the error is happening. But more importantly, it's going to allow you to fix those errors without having to do a reset within your system. So this is crucial for this type of feature is going to be crucial for those applications that we mentioned earlier. So essentially, by incorporating this ECC feature into our memories, it's going to increase the robustness of the memories, and it's going to decrease the likelihood of the systems failing throughout the lifetime of the product. Okay, so that's the first thing that is going to be a problem. The second problem is going to be hackers. So I think we can't really talk about a reliable system without talking about security, right? In order to really have high function of your device and to make sure that this device is working at its peak level, you want to make sure that no one's tampering with the device and changing either the information getting stored in the device. It's been known that hackers can either go into your memory, steal some of that information within your memory, maybe exchange that information that you have in there, and maybe change the operation of the device by injecting code and so on. And also, whenever you're communicating, hackers tend to replace the packets and send false information to the receiver end. So this is another big issue that we have to really think about whenever we're putting together our product. Now, going here to the solution for this, a very good solution for this is going to be making it harder for hackers to really do any type of tampering within your device. And what that's going to require a suite of security features in your microcontroller, things like encryption engines, cyclic redundancy code to be able to make sure that the data being transferred is getting received with any type of changes, secure bootloaders as well to make sure your application is booting up with the code that the owner of the device loaded into the part, and not some type of third party injecting code in there. And the second thing, to make sure that only the people that are allowed to load code into the part are the ones loading information or loading firmware into the microcontroller. And then moving on here, the true random number generator is going to be a big thing to make sure your keys, your encryption keys are going to be created with that are going to be strong keys. You're going to need a strong true random number generator for that. And then the last thing is going to be making sure that the storage where you're putting these keys, this private keys that you own, are put within a non-volatile storage, so that hackers can't really mess with it And this also alpha particles are not really changing the key itself. So with that, now that we really understand the different scenarios of where this could happen, as well as some of the issues that are causing these failures within our systems, I'm gonna introduce you to you guys the Max 32670. This is our, like I mentioned, our newest low power micro. This is the block diagram. And I kind of want to highlight a few things of this device that is really going to help you guys really build a reliable system. So the first thing is going to be what we just talked about, the ECC. We incorporate ECC in all our memories. So we have 384 kilobytes of flash in with ECC enabled. We also have 160 kilobytes of SRAM with optional ECC. So the key point here that is a little different from the flash is that you're optionally be able to turn it on and off depending on what you want, what you're desiring to be your ECC option here. So if you turn it on, there's going to be a penalty of about 32 kilobytes, which means that you're going to have around 128 kilobytes of ECC enabled SRAM if you go ahead and turn it on. So just keep that in mind as you guys are looking at the features of this part. And the other thing is going to be the 16 kilobytes cache with also enabled ECC. You don't really have the option of turning it on and off. That's simply enabled the entire time. And then, so that's going to take care of all these alpha particle issues that we've seen in our products, in our devices. And then moving on here to the security and integrity block on the left, this is actually what we call our trust protection unit block. We have a list of features, security features that are just going to make it really tough for our hackers to go into our device and really try to change the operation of our device or try to steal information from our memories. So these are the same things that I mentioned earlier. You're going to have the secure boot ROM, the secure non-volatile key storage, AES up to 250-bit encryption, and the TRNG and the cyclic redundancy code as well. So this is the tools, and this is what's unique about the part. You know, it's really going to allow you to take your system to the next level as far as reliability goes. With these features, you're really going to ensure that your system is running the entire time and that it's going to fail the least amount of times as you have this device on. So moving on here, even though this is important, you know, and this part is very unique at that, at being ultra reliable, the part is actually really good at other things as well. So our Max 32670, we basically incorporated a lot of the knowledge that we've gained within Maxim as we've sold products to the wearable market, the remote control market as well, where these are products that are battery powered devices. And we've gained a lot of knowledge as we've designed our products to really be able to take the power consumption to its lowest levels. So all of that information, all of that knowledge that we've gained in that, we've actually put here in the Max 32670. So you can see some of the features here on energy efficiency. You can look at this, and this is very good as far as if you compare it to other competitor parts. So that's one thing, a good building block that we have on the Max 32670. Moreover, we have smart integration. Within Maxim, we try to put as many features in the smallest package possible. So the Max 32670 actually comes in a 5x5 TQFN as of today. And in the next few months, we're actually going to have this product also available in a 1.8 by 2.6 millimeter package in WLP. And we're basically putting everything from the large memories that you guys saw in the block diagram to you know, the LDO. We actually include an LDO in here, so you don't have to have an external PMIC. And also the high performance features that we have here on the right, like the 100 megahertz ARM Cortex M4F and the high-speed peripherals also available. One thing to note here on the serial peripherals, sorry about that. It looks like my screen got messed up here. Let me try this again. Here, I'm gonna pause here for a second. All right, I'm back. One of the things to note here is that these peripherals are actually pretty high speed compared to our other products. And as far as the normal speeds for this I2C, SPI, and UART, this is above market average compared to our competitors. So very unique for this part as well. And then the last thing, the fourth building block that we have here is strong security. Again, Maxim has a very strong background in security. We've actually gone into a lot of applications within payment terminals. We have an entire product line of microcontrollers that are secure microcontrollers that go into this type of applications, as well as applications within government where the security features have to be really, really high, and they have to be really strong security features. And we've actually, again, incorporated all that knowledge that we've gained throughout the years in this microcontroller with the secure boot, the really good hardware accelerators, the really good TRNG, and the rest of the security features here. So with that, I'm gonna go ahead and go to the next slide where we have actually put together a demo for you guys. Hopefully some of you guys already saw it, and if you haven't, we've actually put a video on this on our virtual booth, so go check it out. And I'm just going to tell you a little bit about it so you get an idea of what we've put together, but we wanted to put something together where you can see the MAX3270 in action. So we put a body temperature monitoring device that allows you to take people's temperatures in a contactless way. And this, I think this is a pretty cool demo considering the situation that we have right now, right? We meant to do that, and essentially the way it works is you approach the device. On the top screen, you're gonna have each of the infrared cameras on the corners are seeing. This information is getting fed into the MAX32670, processed through an algorithm, and then shown in this little screen up here. And then on the bottom, we're going to show the actual temperature, body temperature of the person that is approaching the device. And then as you go back, then that screen on top and the temperature on the bottom go away, and that means that there's no person in front of it. So it's a nice little demo. Here's the block diagram for it. And we've actually enabled ECC in this case, the error correcting code, to make sure the device is working throughout time and there's no type of issues of failing, so that it's running smoothly the entire time. And also we've included a few security features as well. So just check it out, take a look at it. And with that, I'm gonna go ahead and bring this slide, which is my call to actions for you guys. And there's a few things that I would like you guys to do, or that I invite you guys to do. One of them is to check our Darwin family page. We're going to be sending you the links for this in the chat here in a few seconds. Our Darwin family page is going to show our entire portfolio of products. So you're going to be able to see from our really tiny microcontrollers that are a 1.6 by 1.6 millimeter package microcontrollers with smaller memories, all the way to our big boys like the MAX32650, where we have 3 megabytes of flash, 1 megabyte of SRAM, and a lot of high-speed peripherals integrated into the part. So definitely check out if you think that this specific product and reliability is really not something that really is of interest to you guys. We have a full line of products that might work for your application that you guys are working on. And then the second thing, if you did like the MAX32670, check out the product page. We'll also send this to you guys via the chat. And there you're going to be able to find the data sheets, the user guides for the product, so you guys can kind of go more in depth and look at the technical details of the part. And while you're there, you can also order our Max 32670 EV kit, which is going to allow you to start evaluating the part and really see if this is, you're really going to see the potential of this microcontroller for your future application. So with that, I'm going to go ahead and close this my presentation, and I'm going to pass it on to Ben, as we might have some questions from the audience here.
Yeah, absolutely. We do have a couple of questions, and I'd like to remind everyone that it's not too late. If you want to submit questions, you can go ahead and do that now in the question box on the GoToWebinar app. So first question up, the question was relates to the ECC memories, and the question is there any kind of memory or performance penalty for using ECC in memories? And I think you mentioned that in RAM there's a space penalty, but is there any penalty for using ECC in Flash?
Yeah, so there's no penalty in Flash. Like I mentioned, it's going to be ECC is going to be enabled the entire time within the Flash as well as the cache. And as far as like performance of your core, you know, there's going to be no performance penalties there either.
Excellent. We have another question that relates to security, and specifically what's in the secure boot ROM and how do I get to it? If you don't mind, I'll take that question because
Sure.
I've done some work with the secure boot ROM. Secure boot is actually when you reset the part, there is a ROM built in that always takes control. If security features are not being used, then it simply vectors to your application. If the security features are being used, then it validates the image and then branches to the application. If you hold down a particular pin, then it will enter the secure boot loader, and in that case, it expects secured, cryptographically signed packets to be transferred over either a UART interface or a USB interface into the part. So there's really a couple of different functions in there. One is validating the boot image, and the other is the actual loader function itself. Let's see, we've got one more question here. The question is about software development tools. What's the software development environment like for the 32671, and how do you get the tools?
Yeah, so if you go to our website, to our product page, and you go under the tab Design Resources, we have our SDK. This is actually our software development toolkit, and you can actually download it from there. You're gonna see a bunch of libraries and example code for both the Max 32670 as well as some of our other microcontrollers. It all comes within one package, so that you guys, it makes it easy for you guys. And yeah, just go there, download it, and then you can start. As soon as you have the EV kit, you can actually start running some of those examples to really see how the part really works.
All right, very good. I don't have any more questions right now. I'm going to wait for just a minute or so for any last minute questions to roll in, which one just did. So the question is, how do we verify that the booting has performed the right function intended and doesn't break the ECC mechanism? So I guess the question is, I don't know if this is related to the boot ROM specifically, or if it's related to the image. But I think the question has to do with you know, how does the ECC mechanism work? And I can take that if you'd like.
Sure, take it away.
Because the ECC is one of those things that's really simple in concept, and basically what it does is it creates a parity across subsets of the instruction word. So we have a 32-bit instruction word. We do a parity across all of the even bits. We do a parity across every group of 2, then a parity across every group of 4. That gives us a syndrome, and the syndrome will tell us if a bit reads incorrectly. What is the what is the which bit was in error. Once we know which bit is in error, we can simply change that bit back. For multiple bit errors, for 2-bit errors, it will tell us that there is an error, but it won't give us the location. So in a case like that, we can simply raise an exception and go to some kind of a error routine. But in most cases, single bit errors are corrected transparently, and you don't have any. You're not even aware that an error has been found, fixed, and execution is proceeding as normal. Okay,
Yeah, one
let's
thing to note there, sorry to
go ahead.
interrupt, Ben, but the other thing that I would like to point you guys to, Ben actually put together a really nice video on ECC, and he has some visuals of how this technology works. So if you guys go to our Maxim website and go to the video section, look for error correction, and you guys are gonna see that video where you can see how ECC really works within our microcontrollers, and goes a little bit more in depth.
Yeah, and we have a question here. There's one of our participants is having some difficulty locating the 32. Well, they say 32570. I think this 32670 EV kit is the one we're talking about today. So if you could post a direct link to that SDK, I would appreciate it.
Yeah, we can do that. And in fact, if you guys have any other specific questions that we're not able to get to you guys right now, we do have this email that we're using to answer any additional questions. So if you want, you can send us an email here to eventsteams@maximintegrated.com, and we'll go ahead and send you that SDK link, the direct link to the SDK. No problem.
Okay, I'm going to wait just a few more seconds to see if we have any more questions coming in, and then we'll wrap things up.
While we wait for those questions to come in, if any, we will also send you a copy of this presentation to you guys. In case you want to check out the block diagram or anything else that you might have missed, you guys will get a copy of that too. And in fact, I think you guys should have already gotten it in the handout section of the GoToWebinar application here.
Okay, we have one more question about ECC, and the question is, and it's a good question, is it possible to configure ECC to automatically correct more than one bit? The answer is no. That ECC systems it's a fairly thick chunk of logic that lives in there, and so what it's doing is it's performing that function I was talking about, where you take a parity over the even bits, then groups of 2, groups of 4, groups of 8, and then the lower half and upper half. That gives you the location of the error. Now, would it be possible to create a logic system that would correct more than one bit? Yes, it would. That's not what's in this system. Now, what's the likelihood that you're going to run into more than one bit due to a soft error? And the answer is pretty vanishingly low. We'll detect that error, and then you can take whatever action you need to do to fix the error and proceed with your action. But that would be a software function, not a hardware function in that case. So okay, I think those are all the questions that we have. I'd like to thank Carlos for talking to us about reliability in microcontroller-based systems, and thanks to everyone for attending. If you'd like to learn more about these products, just keep an eye out in the chat. In fact, I see that they have posted the links in the chat already, and you can go to those links and get more information. If you have other questions for Carlos or for me, You can reach out to us at eventsteam@maximintegrated.com or just visit us online at Maxim Integrated. And we'll see you next time.